Okay, the lab that we're going to talk about now are boundary layer flows. And so what we have to remember is that as flow goes over an object, in this case, or in the lab, we're going to be looking at flow going over a flat plate, there's going to be some friction between the plate and the flow itself. And that friction is going to slow down the fluid, right? And then there's a transfer of that slowed down momentum between subsequent vertical fluid particles. And so what you wind up developing is what we call a boundary layer region, right, which is, I'll highlight here in red, where the height of this region where viscosity is dominating is given the symbol delta, and it increases with downstream distance. Now, the flow will start out laminar and then eventually, if the plate is long enough, transition into turbulence. When the flow is laminar, you can see the fluid particles entering into this region, and because of friction, developing some shear, which is distorting the shape of that fluid element. And then eventually, as the flow progresses further and further down the plate, the Reynolds number reaches a critical value where the flow becomes turbulent, and that turbulent creates turbulent mixing where the fluid elements are tossed and turned and shearing a lot and get highly distorted as depicted in this image. Okay. Now, outside of the boundary layer, the particles are far enough away where they don't really feel the effect of, of friction caused by the plate. All right. So the boundary layer has this velocity profile where we have the no slip condition at the wall, right? And the further away from the plate I get, the faster and faster the flow becomes, until eventually, when I'm at the end of the boundary layer region, the velocity there is the same as whatever it is in the free stream. And so you see that the velocity profile becomes flat, right, or a constant value. Now, as the flow progresses downstream, of course, since that height gets larger and larger, the actual profile itself is going to be changing accordingly. All right. One interesting thing to note, we'll show in a little bit, is if we non-dimensionalize these profiles, though, in the laminar case, they tend to collapse, or they collapse into a single profile, which we call the Blasius solution. Okay, so here are the equations that are typically solved, right? These are the Navier-Stokes and continuity equation with particular boundary layer assumptions. If the flow is laminar, we can solve this, which is again called the Blasius solution. We're not going to go into too much detail except show you the results that came from this. Is that if you have a laminar flow, the boundary layer height, which we'll call delta L, can be calculated as being 5.2 times the square root of the kinematic viscosity nu times your position x divided by the free stream velocity. All right, and the velocity profile can have this cubic, or can be approximated by this cubic relationship. All right, so where v over v infinity, non-dimensional velocity, is equal to 3/2 times the non-dimensional height, where y is the vertical height off the wall, and again, delta is the local boundary layer height, right? So let's say at this position, this is delta, right? Minus 1/2 that same non-dimensional height raised to the third power, okay? Now again, what I was mentioning earlier is if you look at dimensionally, these two velocity profiles look different, but if you non-dimensionalize these profiles, both of them collapse into a single shape, right? And that is the Blasius solution, which is gained from a process known as a similarity solution to the differential equation, right? Now, if the flow is turbulent, though, there's no analytical solution. We rely on some experimental data and some matching to that data, and you can come up with a boundary layer height that's equal to 0.37 times x divided by the Reynolds number raised to the 1/5, and the turbulent velocity profile is approximated by that 1/7 power law. okay? And so what we're going to be doing in the lab is we're going to be taking a flat plate and we're going to be placing probes, pedostatic probes, at varying heights. And at each one of these positions, we're going to be able to get the local velocity, right? And so ultimately, we're going to be able to determine what this profile is. We're going to measure that the velocity is higher the further away from the plate we go, and slower the closer to the plate we are. And we're going to compare that velocity profile that we get experimentally to what's expected for laminar and turbulent flow. And we're going to try and figure out what the critical Reynolds number is for our plate. Remember, the critical Reynolds number is this value of the Reynolds number below which we would expect laminar flow and above which we would expect turbulent flow. Okay, so we're going to take these probes and we're going to move them to the front of the plate. We're going to move them to the middle of the plate. We're going to move them to the back of the plate, and we're going to change the flow speed in the tunnel to give us 6 different Reynolds numbers to determine how these velocity profiles change with Reynolds number. And again, we're hopefully going to try and collect some data in a laminar regime and some in a turbulent regime. The critical value is typically taken to be somewhere between 3 and 5 times 10 to the 5th for flow over a flat plate. But we do want to see what it is in our particular setup here.